Hello dear viewers. In last lecture we have learned the RSA algorithm. So now in this video we are going to learn the theoretical implementation of RSA algorithm. So we are going to assume some values and putting in this whole scenario so that we can understand the working of a RSA algorithm. So in the previous lecture, let's make a brief review. We are having this following steps. Take two prime numbers and we are going to compute the m by multiplication of these two prime numbers. Phi n, that is equal to p minus 1 into q minus 1. That is our whole first step. In second step, we are finding a e, that would be GCD of e, and this phi n would be 1. And in the third step, we are going to find the d, and the relation is d is equal to e inverse for phi of n. So now here we are having the three things n, e, and d. So now we are going to make the combination of this n, d, and d to make a public key and a private key. So here now we are having all these set of values. Now here we are going to share e and n to the RS, and now RS is going to encrypt its message with the e and n. E and n is acting as public key of a bomb. So now RS is encrypting that message with e and n, and now that message m is converted to the c, and the conversion method is m, which is the original message, that m raised to power e mod n, where e and n we are using from a Bob. So now this message is sent to the Bob in an encrypted form. Now Bob is going to decrypt it as the m congruent to c raised to power d mod n. So this is our whole scenario. So now let's take some values of the p and q first. Now having the same scenario over here. Now let's take p is equal to 7, p equals to 7, and q equals to 11. So we are performing the very first step over here. So now let's calculate n. So n, that is equal to p into q, and that is 7 into 11, 77, whereas phi n, now this is a phi n, we are going to compute the phi n, that is equal to p minus 1 into q minus 1. Here p minus 1 is 6 into q minus 1, that is 10, whereas phi n is 60 over here. So we have calculated n and phi n over here in the first step. So now let's find the e. So this is our second step. We are going to find the e. Now e, the value of e should be between 1 and okay, here should be greater than, e should be greater than 1 and less than phi of n. Okay, so now here let's take a GCD of e comma phi n is 60. So now you are going to choose any values between 1 and phi n, who is going to satisfy that GCD of these two things would be 1. So for 2, GCD is not 1. Similarly for the 3, 4, 5, 6, 7. Yeah, 7 would be the minimum number for the e. So here I am going to take e as a 7. You can take any higher number if you want, but that is the minimum number which is satisfying this GCD condition. Okay, so now here we find the e. So now let's find the d. Our third step is to find the d. With this e and n, we are going to make a public key. So now d and n would be our private key for the Bob. Here is ns. So now the third step is to find the d. D, that is equal to e inverse, that is 7 inverse e inverse mod phi n, mod, whereas phi n is 60. So now here we are going to apply the modular arithmetic, which we have learned in last lecture, and we are going to apply the extended ruler theorem to solve this. So I am going to use this space to solve this with the extended ruler algorithm. extended ruler algorithm just to solve this equation. Okay, so here we are going to take 60 and a 7. So if I'm going to divide 60 with the 7, that would give me 7, 8 7s are 56, and a remainder is 4. 7 into 8 plus 4. That is our first step. We have to do this 60 and a 7. So now here again we are going to take this 7 and a remainder. So we already discussed this this solution in a modular arithmetic. That would be 4 into 1 into 3. Now taking 4 and 3. 4, that is equal to 3 into 1 plus 1. So here we are having a 1. Now whatever the minimum remainder you will have over here, it means that is the GCD of these two numbers which you have taken, that is 60 and 7. Initially we have took this 60 and 7. So 60 and 7 have a GCD 1. So it means our calculation is fine up to here. So now the next step is that we are going to rearrange this. 1 that is equal to 4 minus 3 into 1, that is 3. I'm just rearranging this. 1 that is equal to 4 minus 3. So now putting the value of the remainder in the same equation. So here I'm going to put the value of 3. 3 that is equivalent to 7 minus 4. So we are going to here not going to solve any of these arithmetic. Rather we are going to grouping these values. Like 4, we are going to group the 4 over here. So here 4 minus 7 plus 4, that make up 2 into 4 minus 7. So that is equivalent to that. 2 into 4 minus 7. So now here we already substitute the value of 3, that is 7 minus 4. Now we are going to substitute the value of 4 over here. Where 4 is 60 minus 8 7 are 56. Here 2 into 61, that is equal to 2 into 60 minus 56 minus 7. Right? Again, we are going to club all the values. We are going to make everything as a 60 and a 7. Okay. So here, okay, we are not going to solve this. So here that would be not a 56. Here would be 7. Okay. Let me change the marker. Here that is equal to 7 into 8. 7 into 8. That is okay. 60 minus 7 into 8. We have put this 4 over here. Here minus 7. So this would be our equation. So now here we are clubbing these 60s and 7. That is equal to is 2 into 60 minus, okay, it's a multiplication, that is 2 into 8 into 7 minus 7. So here we will having this value. So here we are going to solve this. Okay, that would be, okay, 1 that is equal to 2 into 60. Here we will having okay, 16 minus 16 into 7 minus 7 minus 8 to the 16. 16 times 7 minus 7. Taking 7 okay, minus 7 common from both sides. We will having 16 plus 1, that is 17. Okay, 2 into 60 will remain over here. 1 that is equal to this one. Now we are going to take look what we need, mod 60. We are going to take a modulus of 60 from the both sides. 1 mod 60, 2 into 60 mod 60, that would be 0. If we divide this with the 60, it will remain the 0. So we are having a minus 7 into 16 plus 1, 17. So here we are going to find what the inverse of a 7. So 7 is in a multiplication over here. That is going to be divided in this side. Now we will have minus 17. Okay, taking mod on the both sides, I forgot to write mod 60 over here. Mod 60. So now here I can write 7 inverse mod 60, that is equal to, now we are going to calculate this, that would came up to 60 minus 17, 43. Okay, so we will have this whole value evaluated to 43. It means our D is equal to 43 over here. So we have used extended ruler algorithm to solve this inversion, modular inversion relation. Okay, so here I am going to erase this whole calculation. So now here we will having the N, E and D. We are having a value of D, E and N. So here we are going to make the combination of private and a public key. So here I am going to share a public key which I will going to create it with the E. So let's suppose the Alice is trying to send some message, that is, let's say 2. Fine. Now here the encrypted message, that would be m raised to power e mod n. Okay, so here 2 raised to power, the value of e is 7, the value of n is 77. 2 raised to power 7 mod 77. So here we are having this value 248. We are having a 128. 2 raised to power 7 is 128 mod 77. If you will going to divide this with the 77, but we will have 140, so it would be 177, 718. Okay, 75, 12, 51. So here we will have this congruent relation. C is congruent to this, and that would be 51. So our this secret message, that is 51 mod 77. So 51 is the message to send. Okay. So now Bob has created 2 key and shared its public key so that Alice can encrypt the message. Alice has encrypted the message. So this is the message. So this is going to be shared with Bob 51. That is 51. Okay, so now Alice, Bob is going to decrypt the message over here. So how it's going to decrypt the message? That would be C raised to power D mod n, mod n. So that came up to what is C? 51 raised to power 43 mod 77. So now this thing we are going to compute right now. Okay, so now we have implemented all the steps of the RSA algorithm. Now we will have this value, and that would be equal to m, plain text m. So now our m, that is equivalent to this whole equation. So this is our answer. But to solve this, it's very complex calculation. So to solve this, we are going to apply the Chinese Remainder Theorem. So remember that we are having a m is equal to 2 in this case. So now I am going to erase everything and we are going to solve this equation only. I hope you got all this. Okay, now we have to solve this equation so that we will have a 2 as a result. So I'm going to rewrite that thing at this side, m that is equal to 51 raised to power 43 mod 77. So now in the Chinese remainder theorem, we have learned one special case. Okay, that special case is if this mod n is the multiplication of two prime numbers. Here we are having a 7 and 11. Now, if this is the case, we can write this m equivalent to 51 raised to power 43 mod 77, that is congruent to 51 raised to power 43 mod 7, and further that is congruent to 51 raised to power 43 mod 11. So, rather than calculating this complex task, we can divide our task into the two equations which is congruent to m. Okay, so now we are going to solve these two equations. Okay, m that is equal to 51 raised to power 43 mod 7. So let's solve this. And for the m is equal to this one and m is also equivalent to this one. Okay, 51 raised to power 43 mod 11. So we are having these equations. So now the first step is to reduce the base value. Right? We are going to reduce this. So 51 divided by 7, 7 7 is 49. 15, we are having a 2 as a remainder. So here I can write 2 raised to power 43 mod 7. Okay. So similarly we are going to reduce this 51. Okay, 51, 11 4s are 44. We are having a 7 over here. Okay, 7 44. Okay. So here we are having a 7 raised to power 43 mod 11. We have reduced on the basis of this base. When we are going to divide this 11, we will have this remainder, whereas remainder the power would remain the same. So here we are going to apply the Fermat's little theorem. Fermat's little theorem. So now what the Fermat's little theorem says that n raised to power p minus 1, that is equal to 1 mod p. So that is the Fermat's little theorem. So we are going to exploit this thing to reduce this equation. So now here these two are the prime numbers, already prime numbers. So here we are going to make this power in the multiple of 1 less than prime. So here we are going to have 2 raised to power 6 into something. So let's see, okay, here 43 divided by 6, it's 42, 7 6 are 42, and we will have a remainder 1. So here I can write 2 raised to power 6 into 7, and this is plus 1 mod 7. So similarly over here we are going to reduce this 43 with the 11 3s are 33, 0, 1. We will have a 10 over here. Right? So I can write this 7 raised to power okay, sorry, here that should be 1 less than the prime number. Here, this is the condition. So it should be 10. 10 4s are 40, and we will have a remainder 3. So here I can write 10 into 4 plus 3 mod 11. So now we can apply the Fermat's little theorem on these equations, as this is mod 7, that's the prime number, and n raised to p minus 1, that is giving you the remainder 1. So here 2 raised to 6 mod 7, that will give you the remainder 1. Okay, So 1 into, okay. First we have to cover up this. So that would be 2 raised to power 6 raised to power 7 plus, not a plus, that would be multiplication 2 raised to power 1. So when we are going to multiply this, the base would be added up. So we are going to split that thing first. Now mod 7. Similarly here 7 raised to power 10 raised to power 4 into 7 raised to power 3, both mod 11, both mod 7. So here we can directly apply this, that will be 1 raised to power 7 into 2. Okay, you can write it separately, mod 7 into 2 mod 7. Okay, so here again we will have 1 raised to power 4 into 7 raised to power 3 mod 11. So here 1 raised to power 7 is 1 mod 7 is 1 into 2, that would be 2 mod 7, and here we are having a 7 into 3 mod 11. 7 sevens are 49. Okay, let me do over here. 7 sevens are 49 into 7, 63. 343. So here we will have 343 mod 11. So here we will have these two values over here. So now if you remember the Chinese remainder theorem, now you can directly apply the Chinese remainder theorem on these two reduced equations, and you can find the value of x. Okay. So let's again erase this to apply the Chinese remainder theorem on these two equations. So here we will have 2 mod 7 and okay, let's solve this. 343 mod 11. So here we will have 2 mod 11. So that is congruent to 2 mod 11. So here we are having a 2 mod 11. So you can see m is congruent to this one and m is congruent to this one. Okay. So here m equal to x. Actually, your Chinese remainder theorem we have used x. So it doesn't matter. You can use any algebraic variable. So 2 mod 7 and 2 mod 11. If we will divide 343 with 11, we will have remainder 2. So that's why we will have 2 mod 11. So now we are going to apply the Chinese remainder theorem to solve this. Okay. So in Chinese remainder theorem, the first step is finding A1. So this is your A1, this is N1, this is your A2, this is your N2. So here A1 is equal to 2 and N1 equals to 7, whereas your A2 equals to 2 and N2 is equal to 11. So these are our values. So the second step is find the capital N, that is N1 into N2 in this case, that is 7 into 11, that is 77. So now the third step is to find y1, that is equal to n into n1, that is 77 over n1 is a 7, that is 11, and y2, that is equal to 77 upon 11, that is equal to 7. So y2, these are the values of y1 and y2. So now the fourth step is to find z1, and your z1, that is equal to y inverse mod n1. and z2 that is equal to y1, y2 inverse mod n2. So that was the implementation of Chinese Remainder Theorem, the general one. So here we are going to solve these two equations. So z1 and z2. So let's put the value. Y1 is 11 inverse mod n1 is 7, and here y2 is 7 inverse mod n2 is 11. So now again we are going to apply the standard inverse algorithm to solve these two equations. So let's take a 11 and a 7. 11 that is equal to 7 into 1 plus 4. Now taking 7 and a 4, 7 that is equal to 4 into 1 plus 3, 4 and 3. I think we already did this. Okay, so that would be 4 is equal to 3 into 1 plus 1. So 1 is the remainder, GCD of again 7 and 11. So we can rewrite 1 is equal to 4 minus 3, and putting the value for 3 is 7 minus 4, clubbing this 4 minus 7 plus 4, that is 2 times 4 minus 7. Okay, putting the value for 4, that is 2 into 4 is 11 minus 7, 11 minus 7 minus 7, that is equal to 2 into 11 minus 2 into 7 minus 7. Multiply 2, okay, fine. 2 into 11, if I will take the minus 7 common, we will have a 2 plus 1, that is 3. Okay, so here we will have 2 into 11 minus 7, 2 1 3, 7 into 3. So here we will have this equation. So with this equation, 2 into 11 minus 7 into 3, so we are going to take a mod 7 to solve this z1, and then mod 11 to solve this. Okay, so okay, let's play this. Applying the mod 7 from both sides, 1 mod 7, 1 mod 7, hope that would be visible. 1 mod 7, this would be the 0, that is 2 into 11 mod 7. Mod 7 we need 11 inverse, so 11 multiplication, that would be inverse over here, that is 11 inverse mod 7, that is equal to 2 mod 7. So here we will have 2 mod 7, it means that is equivalent to 2 over here. So similarly, taking a mod 11 from both sides, 1 mod 11, that is equal to, that term would be 0, and we will have a minus 7 into 3 mod 11. So here we will need 7 inverse, 7 would be inverse in this side. Now we will have minus 3 mod, we have to mod 11, okay, mod 11. So minus 3 mod 11, so we 11, minus 3 mod 11, minus 11 plus 11, 11, minus 7, it should be 7, so 7, change the sign, 8. So we will have 8 over here. Z1 and this is Z2. Okay, so we have calculated A1, Y1, Z1. Okay, fine. So now the last step is that finding the x. Fifth one is finding the x. X that is congruent to the summation of A1, Y1 and Z1 and A2, Y2, Z2. So A1 is 2 into Y1 is 11 into Z1 is 2. Multiplication of this plus A2 is 2 into Y2 is 7 into 0. If you are having some confusion regarding this, you can watch by that video of a Chinese Remainder Theorem. Then that would be crystal clear to you. So okay, here we will have a mod capital N. Mod capital N is 77. Mod 77. So here we will have 2 to the 4, 11, 44 plus 8, 7, the 56. Okay, 56 into 2, 56 into 2, 112 mod 77. So 112 plus 44, 156. So that is congruent to 156 mod 77. So let's calculate this. 156 mod 77. 77 to 154. So that we will have a remainder 2. So that is congruent to 2 mod 77. So x is equal to m. So you can write x equal to m, that is equal to 2 mod 77. So 2 is our answer. So this is the theoretical implementation of RSA algorithm. So you can, if you need some notes, you can find the link in the description. You can download the PDF, and if you are having any doubt, you can put your question in the comment section below. Okay, thanks for watching. If you like my videos, you can subscribe to my YouTube channel so that you will have latest updates. And thanks for watching.